Alright, it is time to prepare for your limits and continuity test. The first section is all about the definitions. Use pictures to help you if you must. A limit is just a number that a function comes close to, meaning a number, the y value, should probably be included in there, as x approaches a point C from both sides. So if you want a little picture just to kind of help you, as you have a function going from both sides, approaching this point, say that's point C, this is what your limit would be. The limit is whatever you are approaching as you get close. Now the squeeze theorem, this is where we had, say, a function like this and a function like this, and then we had this other function in the middle that's always between them. If these two have the same limit at this point right here, then the middle function must also have that same limit. Use that picture to help you. Intermediate value theorem, same idea, if I can find a place to draw it. Intermediate value theorem is that if you have a continuous function, so here's a and here's b, so then here are the function values, f of a and f of b. That means that no matter what, because it's continuous, I have to hit every single point in between. So if I have a point here that's k, that means somewhere in this spot there has to be a point c that gets hit at that time. Alright, when does a limit not exist? Unbounded behavior, that's like asymptotes. Oscillating behavior, that's where it just zigzags real quickly. And the limit from the left, not the same as the limit from the right. So I could also have written that, so as you approach C positive is not the same as you approach C from the negative. Alright, three requirements is that the function must exist, that's the bridge. The limit must exist, you must be approaching the same spot. And three, the place you're approaching must be where the bridge is. Number 6, the difference between removable and non-removable. Removable is where you have the holes. That's where things will factor out. Make sure you remember that part. Non-removable, that's where you have asymptotes or jumps. That's when you can't factor anything out. And the IVT does not work if the function is not continuous to begin with. That's the first and main rule for that. Alright, now to the actual problem. So this first one, all you're doing is plugging and chugging. When you plug this into your calculator, you should plug in 0.9 and get 1.9. You get here 1.99, 1.999, 2.001, 2.01, and 2.1. What you're looking for is whatever this number looks like it should be. Looks like you're approaching the number 2. So that's why your limit there is 2. On to the next page. We first want to know what the function value is at 2, f of 2. So I look at 2, where do I have the closed dot versus open dot? It's right here, that's why my function value is 3. Now the limit as I approach 2, so as I'm getting closer from this side and from this side, I'm not approaching the same spot, so I do not have a limit. My limit does not exist. Now when I look at f of 7, I look here, I have an open circle. There's no dot anywhere, so the function value in 11 here does not exist. However, the limit in this case, as I approach it, I am approaching the same y value here, and y value is 2. So my limit does exist in this case. Alright, add another one. For this one, g of 3. Same idea, I have an open circle, no closed circles anywhere, so g of 3 does not exist. The limit as I approach 3, though, it's approaching the exact same spot. The y value there is -4, so my limit is fine. For g of -1, I have open circles, I do have one closed circle though, so g of -1 is -1. And as I approach -1 though, here I'm going up to 2, and here I'm going to -4. So my limit is not the same from both the left and the right, so I do not have a limit at all. Alright, in this one we are determining limits again at the various points. In this one, the first one, we have unbounded behavior here. We have an asymptote. The left and the right not going to the same spot. One's going way up, one's going way down. So this limit does not exist. We're going to say this is because it is unbounded behavior. Number 18, as I approach here, I am approaching the same spot here. And this spot is at x equals 4. Or I'm sorry, y equals 4, that's my fault. So my limit is 4. In this one here, my limit from the left is approaching 2. My limit from the right is approaching positive 2. From the left was -2. So I'm going to say that the limit as I approach 0 from the negative side is not the same as the limit as I approach it from the positive side. Therefore, my limit in general does not exist. And this one, when I have this zigzagging action right here, this is going to be a non-existing limit as well, and this is because of we have an oscillating function at that point. It's just going back and forth so much we cannot say where it's officially approaching at that time. Alright, now solving them analytically. This is where we're going to have the most fun, I'm sure. Okay, first step always is just try to plug in. So if I plug in, I get 0 up top, I get -4 on the bottom. Hey, that's allowed. That's not an indeterminate form. My answer here is just 0. In this one, when I plug in, I do get 0 over 0. So I need to try to factor the top and the bottom. So this is the same as the limit as I approach 0 of, the top stays the same, I'm going to factor out an x on the bottom, and I'm left with x minus 49. Well, now notice my x's would cancel out. I can rewrite this as the limit as we approach 0 of 1 over x minus 49. Now I can plug in x equaling 0. When I do that, I should get an answer of 1 over 49. That should be -1 over 49 as my answer. In number 23, I'm just going to try to plug in immediately because this is continuous everywhere, so the limit should always exist. Sine of pi over 3 is what? You better know it. Root 3 over 2. And 24, if I plug in, I'm going to get 1/3 minus 1/3, which is 0, on both the top and the bottom now. So, what I need to try to do is to make a common denominator. So, on top, my common denominator is going to be 3 times the quantity, 3 plus x. To get that, I need to multiply the first one by 3, and the second one by 3 plus x. All that is over x. Now remember, what I can do, because I have a denominator in the numerator, I can kind of shift that downward. So this is what we're going to have. First on top, I'm going to simplify it. I'm going to have 3 minus 3 and minus x. The 3 minus 3 will cancel out. I'll be left with minus x. On the bottom, I'll have a 3. I'll have a 3 plus x. And I also have an x. And as you probably saw, the x's will cancel out. So that means I'm left with just -1 on top, 3 times 3 plus x on the bottom. Now I should be able to plug in. I want to plug in x equals 0. So when I get that, I get 3 times 3 on the bottom. So my answer is -1 over 9. Okay, moving on to these ones, number 25. Where I have the square roots, I'm probably going to have to rationalize, but check and make sure. I do have, I would get 0 over 0, so I do need to rationalize. To rationalize, I'm going to multiply by the same numerator, except instead of minus this last part, it's going to be plus that last part. And I'm going to do the same on the bottom. When I do that, this is going to mean that when I FOIL that out, remember, think FOIL here. When I do that, limit as x approaches 0 of, I'll have 2 plus x, the square roots will cancel out. My inner and outer terms will both cancel, and I'll just be left with minus root 2 times root 2, which is root 4, which is just 2. On the bottom, I want to leave it factored. X times this square root, 2 plus x plus the square root of 2. Okay, if I simplify it, on top, the 2's will cancel out. I'll have just an x left. X times square root of 2 plus x plus root 2 again. My x's should cancel out, and I'm left with, now I can plug something in now that I've canceled out my x's. I'll plug in that 0, and I will have 1 over square root of 2 plus the square root of 2, or 1 over 2 square roots of 2 as my answer. In 26, I again get 0 over 0. So what I need to do is to factor. So this is the same as the limit as we approach 3. My top will be x minus 3, x minus 1. My bottom is x minus 3. X minus 3's cancel, and I get, when I simplify that now, x minus 1, now I can plug in my value of 3. So I get 3 minus 1, which is an answer of 2 for my limit. Alright, we have another rationalizing in number 27. I'm going to multiply by x plus 1 over x. When I do that, it's going to simplify to be the limit as x approaches 0 of, well, let's find out. Top is going to be just x plus 1 when I do the first. When I do the outer and inner, they cancel. I'll have just minus 1 when I do the last, over the quantity x times, well, it would help if I would write this right. X plus 1 should be on the bottom there as well. So it should be x plus 1 plus 1. All right, my 1's on top will cancel. I'll be left with the limit as x approaches 0 of x over x times the quantity square root of x plus 1 plus 1. My x's should cancel out. No surprise, that's what we expect. And I'm left with the limit as x approaches 0 of just 1 over this quantity, x plus 1 in the square root plus 1. Now I can plug in, and I should get my plug in 0. That's just the square root of 1, which is 1. 1 plus 1 on the bottom is 2. And I have just 1 on the top. So 1/2 is my answer. All right, in 28, when I plug in, what I need to do for piecewise is just plug in 2 for each. Plug in 2, and when I get that, I should get 2 squared plus 2 times 4, which is 12. In this one, I get 2 cubed, which is 8, plus 2 times 2, which is 4. 8 plus 4 is 12. So the limit from both sides are the same. So that means that the limit here of this function is this value we just found, 12. That's all you need to do. All right, 29. Plugging in, you should get 0 over 0, so let's factor. So this is the same as the limit as x approaches -2 of x minus 5 times x plus 2 up top. I should get x minus 2 and x plus 2 on the bottom. X minus 2, x plus 2. So the plus 2's cancel out. So that's all I'm left with. The limit as x approaches -2 of this quotient, x minus 5 over x minus 2. Now I should plug in. When I plug in -2, I get -7 up top, -4 on the bottom. So a positive 7 over 4 is my answer. And in number 30, if I plug in 2, I should get 2 to the 2 squared plus 1, which is 5. And I plug in here, 2 times 3, which is 6, minus 1, which is also 5. So again, my limit here, as x approaches 2, is 5. Just for example, though, if this was, say, 5 and this was 7, then it's not the same number. Then I would have said the limit did not exist, just as simply as that. All right, determining where we have continuous functions. I'm going to look at 32 first. It's easier to see. Always start at negative infinity, go up to where my first break point is, which is at 3, or at -3, I should say. Start on the other side and go until you break again, which it never does. So -3 to infinity. For 31, starting at negative infinity, my first break point is here at -8. I then went from -8 to my next break point where you jumped here at 4, -4. I went from -4 to this asymptote, which is at +4. I go from the other side of the asymptote to this +8, and then I continue on from 8 to infinity. So that one had a lot of different parts to it, but those are the intervals in which they are continuous. All right, finding discontinuities. First of all, in something like this, I'm not dividing by anything, it's just a polynomial. This is continuous everywhere. This is continuous everywhere, so we don't have any issues with that one. 34, you need to try to factor top and bottom. So this is the same as x minus 4 over the quantity. We have x minus 6, or I'm sorry, x plus 6 and x minus 4. So as you can see, the x minus 4's here would cancel out. Now, what we want to look at, when does my bottom equal 0? That's when x equals +4 and x equals -6. The x equals 4, it canceled out. That meant this was a removable asymptote. The x minus 6 did not. That made it non-removable asymptote there. 35, same idea. Need to factor the top and bottom. On the top, x plus 3 and x plus 4. On the bottom, x plus 3 and x plus 5. So my discontinuities, x equals -3, x equals -5. X equals -3 canceled out. That made it removable. X minus 5 was non-removable because it did not cancel out. At 36, kind of like with the limits, we want to just plug in and see what we get. When I plug in here, I get 2. When I plug in here, I get 1. So they're not the same. So this is discontinuous. It's discontinuous at that point right there. So discontinuous at x equals 1. Nothing cancels here, so this is a non-removable discontinuity. 37, factoring. X minus 2 up top. X minus 2. And, oh, actually, I take that back. I forgot. This is the one that we said to skip because it didn't factor right. You would just, same idea though as these two, try to factor and see if anything canceled If not, well, nothing's going to cancel here, so whatever my two factors on the bottom would be, they would both be non-removable as a result. All right, and 38, just like 36, plug in. When I plug in 2, I here get 2 times 4, which is 8. When I get here, I also get 8. So because of this, and because both of these are continuous to begin with, this function is continuous everywhere, just like in number 33. All right, home stretch, intermediate value theorem. All you need to do is first say, always, 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 is it continuous? 39, yes, is continuous everywhere. Continuous everywhere. 41, also a polynomial down here, is also continuous everywhere. Now, 40, there's a discontinuity when x equals -3. But the interval we're looking at is from 0 to +3. So it's not continuous everywhere, but it is continuous on the range that we want, on the interval that we want. So now, all you need to do from there is find two values for each. We need to find the function value at each. F of 0 and 1 for this one, f of 0 and f of 3 for number 40, and then f of 3 and f of 6 for number 41. And all you need to do is just plug that into your calculator. You should get 2, -1.92, -2/3, 1/6, -1, and 8. And to prove that there's a 0, all you need to show is that you have a number, or that 0 shows up somewhere between these two function values. And then all you should say is, for each one of these, since 0, or I'm going to write it like this, since 0 is between the two functions, so f of 1 and f of 0, then a 0 exists on whatever interval we have. So in this case, from 0 to 1. But pretty much you need to say is continuous first off, and you need to give these two function values and show that 0 is in there somewhere. There you have it. I know it's a lot. Hopefully you're in good shape and ready to make this happen.